I hear you're saying to yourself, wait a minute, I've already seen this one. What is he putting the wrong thing? Nope, no, I know what I'm doing. Trust me. So we're going to talk about electric fields, but as I do a lot, we're going to draw some analogies between electric fields and gravitational fields. Okay. So we talked about this one before. There was some writing that should have been on here before, but that's okay. What we'll add is the following. All right, we know that if we put another mass here, we'll call it M, there's a force on it that we'll call Fg, that's G big M little m over r squared. Okay, now we can also call that little m G, right? Where G is what we've called gravitational acceleration or and gravitational field strength. Okay, so one way to do gravitational field strength is Fg over little m. The other way to do it is that little g is big G, big M over r squared. All right, we're just saying if we take this thing and do Fg, G, big M, little m over r squared, divided by little m, right, that goes away. There's our value of G. Okay, so here are two ways that we've already talked about of expressing gravitational field strength. We can either talk about it in terms of the force applied to a mass in the field, or as a function of the mass of the thing that makes the field and how far apart from it we are. Okay, depends on what you know and what you're looking for. If we look at electric fields, we can say that if we place a charge here that I'll call lowercase q, let's call it positive. Well, there's a force, F electrostatic, on that, where we can say Fe is K times big Q times little q over their separation squared. Now, what we can also say, look at our, we're going to try to make an analogy here, right? We've said this before for gravitational forces depend on the mass of the thing in the field and the field strength. So here we're going to write that as electrostatic force is charge of the thing in the field and the field strength. Okay? Which is going to allow us two expressions for electric field strength. One is its force per unit charge. Now, if we do Fe, which is K, big Q, little q over r squared, and divide by little q, we end up with another expression for electric field, which is K, big Q over r squared. Okay? So those are our two expressions now for electric field strength. All right, what we got to be sure about is Q is a charge in a field made by charge Q. So Q is a charge that makes a field. Now, don't all charges make fields? Of course they do. But the question is, do we want to talk about this Q that's being affected by a field that something else made, or do we want to talk about this Q that makes a field? That's that's going to come with some experience solving some problems. Okay. Okay. So now we can get to here. Blah 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 blah. So did it. Good. Now this one is not in your notes. It's not in your notes, but should be. So do what you need to do to add it in. I can't get rid of that red line over there. I don't know what it is. So let's talk about, we got a positive charge here. Let's just say, I don't know, let's call this 2.5 microcoulombs. And let's say this is, I don't know, 1 centimeter. We want to know the field strength, right? What's the field strength at location X? Well, we're looking for the field made by this charge, all right? So the field here, E, is K big Q over R squared, right? We would not use this one because, well, we know nothing about any force, and there's no charge that we've said we've put there, all right? So here, entirely appropriate to use this expression for electric field because we know what strength of the charge, we know what charge made the field, and we know how far away from that charge we are. Okay? So that's going to be, let's see, 9 times 10 to the 9th. Well, I'll let you just plug in. Yeah, I'll write it out because, you know, I'm a good guy. Let's see, 9 times 10 to the 9th. Newton, nope, yeah, Newton meters squared per Coulomb squared times 2.5 times 10 to the negative 6th divided by 1 times 10 to the negative 2nd meters. Don't forget to square. And we get something like 2.5, 99 times 2.5e negative 6 divided by 1e negative 4. Yeah, 2.10 to the, let's see, give me the old, how do I go to scientific? Well, let's see, 8th, right? Yeah, 8th. Now, units for electric field. Units for electric field. I should go back. Let me see if I can go back to say, what are we on now? Slide 17. Maybe slide 13? Nope, 14. So units of this have to be, well, if you look right here, the units must be newtons per coulomb. Remember how we said that G could be expressed in newtons per kilogram? Same analogy, or using that analogy, instead of force per unit mass with gravity, it's force per unit charge, so therefore newtons per coulomb. Okay? So 2.25 times 10 to the 8th. Come on now. Come on now. Newtons per coulomb. Now, that's the electric field strength. I would say, well, the field, because that's a positive charge, is to the right. Yes? I wish I had done all that work up here. Duh. Now, what's the force exerted on an electron that I place at location X? For whatever reason, I'll do this up here. Well, now we're looking for a force at that a force on a charge that we place in that location. So this says that we go here, E equals F per unit charge, because we're looking for a force, and we know we're talking about an object or a charge that's placed in the field. All right? So we're going to write this as F is QE, just like F equals mg, right? F equals QE. So that force is going to be, well, let's see, charge, well, notice, electron, 1.6 times 10 to the negative 19th coulombs times 2.25 times 10 to the 8th newtons per coulomb. The force exerted on an electron is 3.6 times 10 to the negative 11th newtons. Now, here's the reason, another reason I really wanted to point this, or put this slide in here. So we put an electron here that's negative. Well, that charge is going to feel a force this way. Notice, the field points right. The force on an electron is left. By definition, fields point in the direction of the force that a positive charge would feel. This is a negative charge, it's an electron. It will feel a force in the opposite direction of the field. That's a big thing to point out. I mean, one that you sort of know, but big thing to point out. Negative charges will feel forces in the opposite direction of the field. Okay? Okay, slightly more labor intensive. Let's find the electric field of position x 2 meters. So that's like out here. And y 0. So I'm going to do this. Position x. Well, let's just call it position x. At that spot. That's not a charge. That's a location in space. I'm going to color code here. We do have this one as blue. We'll make this one red. We'll make this one green. Let's find the net electric field at this location here. All right, so blue charge is negative. There's a field like that I'll call E4 that points toward negative charge. Red charge is positive. There's a field like this, E5, that points away from positive charge. Green is also positive. There's a field that points like this, E3, that points away from positive charge. Okay? Our net electric field is E5 plus E3 minus E4, assuming that positive is to the right. Okay, so net electric field is, well, E5, okay, Q5 over R5 squared, plus K times Q3 over R3 squared, minus K times Q4 over R4 squared. All right? If you want. Oops, don't write the K again. I'm factoring out that K. Don't divide it out. Factor it out. Q3 over R3 squared minus Q4 R4. I'm going to pause while I calculate. I get that the net electric field is 24.2 newtons per coulomb. Right. Just so we're sure, R5 is 2 meters. R3 is 1.2 meters. R4 is 2.5 meters. Notice these are nanocoulombs. Nano, nano, nano. Okay? Okay. Next, a little more challenging, this problem. Well, we at least, I don't know, more challenging, but we tie in a couple of different principles here. This one's a doozy. But let's get started. Positively charged bead falls from rest. Okay? We got a bead here. Falls from rest in a vacuum, blah, 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 in a uniform vertical electric field. Okay, so there's a field that this thing is in. It's a uniform field. We're going to get back to that in a minute. We'll talk about uniform fields. You know what? I'm going to put this one on hold. Let's get to the uniform field thing first. All right, this one we talked about today. So yeah, all right. Here's this thing about what we call two charged parallel plates and oppositely charged parallel plates. Well, you might remember that when we looked at the field made by a line of positive charges in the applet, we said that the lines point parallel to that, what do you call it, to that plate of charge, or that, line of charge. We also know that fields get, well, let me just draw that. So, this line of charge over here, these positives, make a field that looks like this. I'm purposely only drawing it over here on the right. I'll tell you why in a minute. The negatives would make the same field but instead of pointing away from them like the positives, the reds are negative, so the field points toward negative charge. Again, I'm only drawing it between the plates. I'll tell you why in a minute. Well, here's a really important fact. How do you tell where a field is strong? Well, let's look at a point charge. Point charge field looks like this, if that's a positive charge. We know the field is strong, say, in here, because the lines are closest together. If you look in here, the lines are always the same distance apart. They never spread out, they never converge. And that means that the field never changes strength. That's a huge, huge point. This is called a uniform electric field. It means constant strength. And direction. All right, just like in this room, there's a uniform gravitational field. Everywhere in this room, the gravitational field is 9.8 newtons per kilogram down. Right? That's what we call a uniform electric field. Now, the direction of a force exerted on an electron. Well, we put an electron in here. Electron's negatively charged. Two ways to tell. Well, one is by the field. The field points right. Fields point, by definition, in the direction of a force that a positive charge would experience. This is a negative charge. It's going to be pushed to the left. And of course it is. Negatives will be attracted to that positive. Negatives will be repelled by those negatives. Okay, so left. What's the direction of a force in a proton? Of course, it's to the right. I'll give you three choices. Let's put a proton here, here, and here. At which location does a proton feel the greatest force? Think. Pause. Return. The answer? It's the same everywhere. Just like saying, at which location in this room does a 1 kilogram mass weigh the most? Well, it weighs the same thing everywhere because the gravitational field in this room is constant. Or is uniform. Okay? Now, an electron's acceleration in this field, well, here's the force. Whoa! Here's the force exerted on that electron. And we could say that that force is QE, or really E times E. Well, that force is also equal to, that's the net force on it. So I should really do this. How about I say that the net force acting on it has to be MA, right? So that means that this is an electrostatic force is M of an electron times A. And that means we can write this as Q times E equals M times A, or really E times E equals MA. So the electron's acceleration will be E, charge of an electron, E, electric field, over mass of an electron. Fair enough? Fair enough. Now, towards the end of these plates, you'll remember maybe looking at the applet, we did get this, what we call fringing at the end. So towards the end, they're not, it's not the same as in the middle, but we concentrate when we talk about charged parallel plates. We talk about the field, between them, the uniform part. All right, here's the other part. Out here, don't draw this. Out here, well, the field from the positives still looks like this. If we assume, especially, and what we do is assume this, that the fields are really, really long, that means that the field will stay uniform almost no matter how far away from the plates you get, especially if they're infinitely long. The field from the negative will look like this, pointing toward negative. And again, it doesn't matter how far away we get from these really, really, really long plates, the field stays the same strength. So what's the net effect of these blue fields away and these red fields toward, the net effect is that there's zero electric field out here. Same thing over here. E is 0. Okay? Real important thing about, what do we call them there? We call them uniform electric fields, especially between charged parallel plates. All right? What else here? Yeah. Now, what do objects do in uniform fields? Well, we know what a mass does in a uniform gravitational field. Since the field always looks, I could represent the gravitational field G like this object will fall in a parabola, right? Where this velocity we call Vx stays constant the whole time because nothing's pushing in that direction. But let me do this. I'll do them in a different color. Here's Vx, stays constant. Our V vertical, our Vy, goes from 0, V initial y is 0, to something little, to something bigger, to something bigger. All right, Vy, Vy, Vy. Well, an electron in an electric field can move in the same, can move in a very, very similar path. All right, let's make it so this electron does this and moves in a path like that. Well, that would have to be because there were negatives down here and because there were positives up here, which means the electric field would have to point like this, from positive to negative. Well, why does the electron go upward if the field points down? Oh yeah, because fields point in the direction of a force that a positive charge would feel. This is a negative charge. All right, this will do the same exact thing. All right, if we call this Vx, and we say here's our electron now, and now, and now, it'll have the same exact Vx. I'll do it in blue. Same exact Vx, same exact Vx, same exact Vx. And now it'll have a V vertical this way, and then this way, and then this way. Vy, Vy, Vy. But it moves in exactly the same shape, a parabola, exactly the same shape of a path that this mass in a gravitational field does. All right, over here, for the mass in a gravitational field, we could say, I don't know, what stuff do we know? Well, we say A in the vertical direction is G. And then we could say, well, over here, A in the vertical direction is E. Right? Remember, we've used this both as acceleration and as gravitational field strength. That's kind of a wild way to look at that, right? We could do more solution in terms, if we, depending on what we ask, we could find different quantities here for how far it went, or how far, what deflection it feels off its straight line path, stuff like that. Okay. Now this has assumed, right, up here so far, all this stuff assumes that electrostatic force is like way bigger than gravitational force. Right? We haven't taken into effect gravity at all. But there's some situation, even for this one, where what if we change the strength of the field such that this thing doesn't deflect at all but still moves in a straight line path? And here we're saying, well, let's really remember that an electron is an object that does have mass. As it moves through this field with a speed v, right, even a field that looks like this, that would make the object want to deflect upward, because there's a force upward that I'll call F electrostatic. Well, at some field strength, that's got to be equal to our gravitational force. Well, we're saying that Fe equals Fg if that path remains undeflected. And Fe we can write as Q times the electric field, and Fg we can write as M times gravitational field. So we want to know what the field strength is. Woo! Well, we just do E is mg over the charge of an electron. Okay? So a lot there, folks. A lot of electric field stuff. This stuff, this page, this slide especially, we're getting pretty into some pretty complicated stuff for sure. All right, but it's important to me that we try to draw these analogies between what masses do in uniform gravitational fields and what charges do in uniform electric fields. They can do the same exact thing. Okay? If we look, come on, dummy. If we look, come on, here, again, we'll leave this problem for a later date. Scratch that. Do it for homework. Do it for homework. Do it for homework. Got that? It's going to be a net force thing, right? We've got a gravitational field. We've got a electric field. And you can write that net force statement. Net force equals ma. Okay? Oh, I guess we don't know, because we don't know what direction the field is. All right? You can assume that, why don't you do this? Assume that it's up. Then you should have some proof if you're right or wrong. Okay? But yeah, these are the kind of bread and butter questions, things in a straight line. We could certainly do them also for things that are at a right angle orientation, net field stuff. Single charges are the most straightforward ones. But this stuff here, we're getting into some great application stuff. Okay? So big range of complexity. But altogether, I think this should give us a good foundation in electric fields. All right? Do that problem for homework. I'll see you tomorrow. And we'll have a quiz tomorrow on, it's Friday, Quiz Friday, on Coulomb's law and electrostatic force. See you, folks.